This is a learning module for section 8.4 of the Matter and Interactions textbook. And in this section we discuss the quantum harmonic oscillator. So the quantum harmonic oscillator is another example of a type of quantum potential that we can solve. So previously we discussed arbitrary quantum potentials or quantum energy systems that had energy levels given by E1, E2, etc. up to En, where the spacing between the energy levels was not necessarily equal. We also had the hydrogen atom, which had a Coulomb potential, and here we had an exact form for the spacing between the energy levels. It was given by energy En equal to negative 13.6 eV over n squared. And now we discuss the harmonic oscillator, which is important because almost every realistic potential can be modeled as a harmonic oscillator near an equilibrium point. So for instance, if we imagine the potential that exists between a pair of atoms in a solid or in a material, we have some potential that looks like this, and near the equilibrium point we get what looks like a parabola that goes like x squared. And so defining, of course, the spring potential energy is 1/2 kx squared, then given this potential we can approximate near the equilibrium point the spring potential. So the difference between the quantum harmonic oscillator, or one big difference between the quantum harmonic oscillator and the hydrogen atom, is that the energy levels of a harmonic oscillator are evenly spaced. So if we have our harmonic oscillator potential, we have a definite ground state energy, and in the harmonic oscillator we label it E0 by convention instead of E1. So in the oscillator, E0 is the ground state, E1 is the first excited state, E2 is the second excited state, and these all have an even spacing. So E0 is given by the quantity 1/2 h bar omega, E2 is given by the quantity 3/2 h bar omega, E2 is 5/2 h bar omega, and in general En is given by the quantity 2n plus 1 over 2 times h bar omega. And so the difference between each of these energy levels, delta E, is equal to h bar omega, and h bar is Planck's constant divided by the factor 2 pi. So h bar is equal to h, which is Planck's constant, divided by 2 pi, and it has the numerical value of approximately 1.05 times 10 to the minus 34, and units of joules times seconds. So clearly joules times seconds times frequency, which is 1/seconds, gives joules, which is units of energy. Okay, so another point to make about the harmonic oscillator is we can look at how this relates to our previous model of an Einstein solid. Remember that in an Einstein solid, where we discussed speed of sound and Young's modulus, we had atoms that were separated by interatomic springs, not real springs, but approximate springs, for the same reason that the potential between two atoms can be approximated as a spring potential. We imagined it this way, and that we had the spring constant for one of these springs given by k sub I, k interatomic. Now in the quantum harmonic oscillator we have the energy, which is again 2n plus 1 over 2 h bar omega, And this omega is still given by the quantity square root of k quantum over m, but k quantum and k interatomic are different from each other. To see this, notice that each atom in this chain can be broken up into a unit like this, where they get half of the spring on either side of themselves. So remember that if one of the, so the idea is that the spring constant for one of these atoms is given by these two half springs. So this half spring is in series with this other half spring. So if we call the half spring spring constant K effective, then for series springs, 1 over K effective plus 1 over K effective is equal to 1 over K interatomic, which tells us that K effective is equal to 2 times K interatomic spring constant. And now each atom has 2 of these springs that are in parallel with each other. So parallel springs add. So Q quantum is equal to K effective plus K effective, or in other words, is equal to 4 K interatomic spring constant. So the relationship between omega and the interatomic spring constant discussed in the Einstein solid is that it's equal to the square root of 4 K interatomic over the mass of the atom in the lattice. And remember that in a three-dimensional solid, each atom has 3 dimensions that it can vibrate in. So this is in and out of the plane. We might say X, Y, and Z. So for each atom, there are 3 oscillators. There's an oscillator at X, an oscillator at Y, and an oscillator at Z. So for a solid with n atoms in 3 dimensions, there are 3n harmonic oscillators. And that's basically the point of the harmonic oscillator. Remember that in the harmonic oscillator, the energy level starts at E0 by convention. It has a definite value of 1/2 h bar omega, and then the spacing between the energy levels is the same for all of them, which is 1 h bar omega. And so in general, you have a formula for En given by 2n plus 1 over 2 times h bar omega.